We will begin the day two of this year's iNaCoMM with two electrifying invited talks. Allow me to introduce our first speaker, Dr. Vineet Vasishtha. Dr. Vineet Vasishtha is an associate professor in IIT Gandhinagar, where he leads the Human Centered Robotics Laboratory. He has a master's in design from IIT Delhi and earned his PhD in mechanical engineering from Columbia University, New York in 2015. Dr. Vasishtha's research program is dedicated to developing novel human centered robotic technologies designed to enhance the quality of life, drawing significant inspiration from the principles of human motor and movement adaptation. His research has attracted substantial funding from esteemed programs and organizations, including the DST's Inspire Faculty Award, SERB's Early Career Research Award, a co-research grant, MHRD Spark, DRDO, LSRB, and many others. Dr. Vasishtha was honored with the Haryana Yuva Vigyan Ratna Award in 2022 and became a member of INYAS in 2023. Dr. Vasishtha, the stage is yours.
Very good morning to everybody. Thank you very much for having me here. Thank you very much for the introduction. It is my pleasure to be here and share some of our work. Sorry, I'm standing on a wooden platform, so I'm looking that tall, so I'm not that tall though. But yeah, I think starting with the work that we are doing. Uh, so I thought that I will present something on um, that's a kind of need of the hour, and hopefully, I think during the presentation, I will try to make that point a little bit further. That why wearable robotics we need to work further more, and why do we need a human-centric approach? It's not just a pure sensor development, actuator development, but it's a need to understand the human biomechanics a little more carefully. So from that perspective, to begin with, so this is I hope I'm clear. Yeah. So to begin with, this is our campus. So we are on a Sabarmati River. So I invite you all. So whenever you are there, please stop by, and I will love to give you a tour around. Uh, we are in Gujarat, so this water is real. It stays till April or so, then it will start drying on. So right now it's full. So this is the best time to visit us as well. So in there we are called Human Centered Robotics Lab, and as the talk sets the moment, so we are working on robotics technology, but we try to use neuromusculoskeletal understanding of human movements per se. So that brings me to the first point, that how do we move? And I think it's a very, very interesting hierarchical structure. If we try to understand, we all work on robotics and mechanism related stuff, we will be able to relate. So the structure is very, very cohesive. So it all starts. Uh, okay, so I am not able to use the cursor, so I will just use it here. So it all starts at the brain level. So if I say my CNS, which comprises of brain and spinal cord, it generates some signals. So basically neurons firing. So I want to grab this water bottle. I think there are some particular signals that are being generated, sent to my spinal cord, and those commands have come to my muscles. And that's where the interesting dynamic starts playing all together. So when muscle contracts, first of all, we will have lot more muscles than I need. So there is an optimization problem that is getting solved, which is recruiting which muscles to use, how much they should be contracted, and so on and so forth. Once that is decided, based on the contraction, joint torques are applied, and essentially I end up moving. Right. So this is how it looks like. It can be put it in another way, where we can think of this gray and this red kind of structure as the mechanics of movement. So there are rigid bones kind of things we can represent, then there are elastic muscle tendon arrangement that is there. So this is the pure mechanics part of it. Then there comes the electronics or actuation or control, that level of strategy, optimization, high level control. That's where my CNS and all these feedback and feed forward loops start kicking in, right? And this, if I try to mimic in a robot, I think it becomes a very involved task. So most of our robots are anyway trying to do this. Maybe some other time we will discuss that the control strategy a human follows versus a control strategy that a robot follows are significantly different, and that makes it a coherent comparison as well. Now, from the human perspective, I touched upon muscles. We use way too many muscles. So this is one simple example. Let's suppose my ankle joint needs to do plantar flexion, dorsiflexion. That's a single degree of freedom joint I'm talking about. It does have multi degree of freedom, but if I just restrict myself to that single degree of freedom, I need at least two muscle collaborating with each other. Think of this cartoon as a mimic of two muscle trying to coordinate together. If both start fighting with each other, there won't be a net output. There won't be a net torque that is going to be applied, which will create the motion. What they need to understand is when muscle A is working, muscle B needs to relax, or muscle B is working, muscle A needs to relax. Or a very interesting situation like you are walking and there is water on the ground, both muscle needs to coordinate to create the joint impedance. So add your stiffness at the joint so that you can actually walk through it properly, right? So these are various versions these muscles are used. So inherently there is a redundancy in human movement system. So we utilize this to work around. As I was mentioning earlier, the forward path is you contract muscle, you generate enough forces, these forces get converted into joint moments, and then that is what we see as a motion that we generate. How do we analyze this in the lab? Is completely reverse. So my apologies, I think the figure didn't come out very clearly, but what it shows is in the lab we go it in the inverse direction. What is something that we can observe is the motion. We use cameras, motion capture system, even IMUs these days to record this motion related aspect. When we record this motion related aspect, we go back a little bit further forward, or inverse rather. We do inverse kinematics, then we do inverse dynamics. So we have to record all the ground reaction forces that are generating. So I'm standing, I'm applying these forces, then I get the joint torques. Then comes the interesting question: how or which muscles are getting recruited? What is the force that is getting generated? That requires another level of problem solving. And here we have not yet connected to the spinal cord, because that's where the motor unit aspects start coming in and work it out. So this is one aspect of it, that the redundant inherentness in my musculoskeletal system. And then comes the motor control. So I need to pick up this bottle. Is this the only path trajectory that I have to choose? Not necessarily. Depending upon if somebody else or there was some obstacle, I would have created another trajectory. But in the absence of any obstacle, I would unconsciously grab the bottle in this way, right? So there is a control strategy, higher control strategy that is been built, that is kind of called as internal model that we have developed. So for example, you might start playing a badminton game today for the first time. You might not be very good at it, but eventually you will try to figure it out, which muscles to use, how to contract. Just like a infant, when an infant start interacting with the environment, he or she is firing each muscles and trying to figure out what are the right neural connections. But eventually they create a neural path, they create a internal model. Okay, to grab my toy, these are the muscle I need to actuate. So the same thing happens. So how there is a redundancy at each sort. Now, what we are talking about? We are talking at this stage of using robots for human collaboration, right? So, why I showed couple of those slides earlier is we need that understanding before we actually start developing these robots for human. A human inherently has redundancy, not only in terms of the choice, the trajectory I am going to make, but in terms of the actuators I have, in terms of the sensors which I can rely on. I can rely on my vision while walking, or I can hear somebody, or maybe with my tactile feeling I can kind of judge what kind of surface I'm walking on. So there is a redundancy in feedback circuit as well as the feed forward circuit. So how do I utilize those aspects? So if I'm creating an exosuit or wearable setup for myself, it will benefit knowing that understanding. So human robot collaboration is going on. There are various aspects to it. One aspect that I would like to show is, of course, not this, but maybe like this, and through the use of wearable robots, right? So the robots could be of various type and configuration, but the kind of robots that I would rather like to talk today is something that I wear and work around. So, human robot collaboration using wearable robotics. So, the kind of approach that I like to share with you is mimicked in this slide. So, we like to see human neuromusculoskeletal system as a set of neuromechanics, motor control, and limb impedance is something we are trying to work on, and I have added. We look robot, of course robots are robots, but I think we look at a special kind of robots called cable driven robots. So there are we try to mimic and understand all different kind of characterization that they have, and finally we try to combine them and like to study them further. The idea is, using this we should be able to explain things as simple as that. Why my 6 years old son, when he goes to the school every day, the first thing he does is wear his bag and stoop forward. Why this was done? The addition of mass and inertia, why it needs to be compensated that way? It's a very simple question. Now let's go to a little difficult question. All of us must have interacted with screwdrivers. Imagine with flip versus a flat head, right? So flat head, how many times instead of screwing the screw in, our hand went here and there? How many times we have spoiled the wall of our home with the hammer trying to get the nail inside? Those all are interaction tasks. They are not active robots, but they are passive system. I'm interacting with it. I'm, as a healthy individual, I'm interacting with it. How I become good at it is through internal model development of that, considering that extra weight in my hand when I'm moving that hammer. Now, when I'm going to put a robot on myself, the human strategy would be the same. Human would still like to make internal model. Human would like to embed it that in their way of doing things, right? So again, understanding these simple tasks. Why when I'm cutting a thermocol with a knife, I always end up cutting it wrong. It never comes like a straight line. Why? This is a non-linear interaction that I am having. How I'm doing it? It's no longer just a matter of controlling the joint torque at the joints. It's more than that. I'm controlling at the joint impedance at each joint, which direction I need to make my arm not go versus go is comes through practice. And what is that practice? That's just the development of a feed forward model that we are creating. And of course, bicycle, we all have done it. Right now my kids are going through that journey, and I'm observing that. So when you do the first time versus when you become good at it, how that experience goes. Not only that, but also to explain, I think, some of these behaviors. So I hope this slides work. So what it shows is, this video is not working, but what in this video you see that there are a couple of therapists interacting with a kid who has cerebral palsy. Now look at this particular situation. Of course, there is an individual who needs our attention, but look at the way the attention is being given. It's an assistance that is being provided to the kid at the pelvis level, at the weight level, and also teaching him how to move the leg. Now imagine a robot doing the same thing, but which just focused on the joint torques or the force that needs to be delivered. It's not gonna be taken. Now, let I put up another simple example. My niece is sitting with me and I'm trying to teach her how to draw a big spiral or something like that. I put my hand on her hand and I try to help her. She might reject my assistance if I appear like a robot, right? We all can imagine what's going on there, right? So if I am not applying those force careful enough, I need to worry about whether those forces are acceptable by the individual. In real time we make that choices. If I try to assist somebody and I see that the person is rejecting my assistance, I remove my hand immediately. Physical therapists do that on the go. When they were assisting this kid, the kid was accepting the assistance. They were forcing to use the hip joint versus the knee joint. That was going on in real time. How do we get that kind of understanding? How do we incorporate that kind of understanding? So in that realm, I think there are a couple of steps that needs to be done. We are doing some iotas of those. Is first try to make the robot redundant. It goes of course out of the common practice that you are making a robot redundant per se. You're making it expensive, you're making extra actuator, but it is an attempt to give that extra ways of doing the same task. There can be other approaches. So to do that, I will share a few slides. Please let me know when the time is close to up. So some of the things that we are doing in the lab is through motion analysis. So the first step in our work is to analyze people doing task. So for that matter, we have been lucky enough to get fundings to create a full gait lab. We have exosuit, force plate, and metabolic consumption. So we can record human motion and recreate it and generate that data. But that's a controlled environment. We will like to go outside and try to do these day-to-day activity. We record human motion data. We use computer vision, sometimes some extreme VR games, so where people are given some dual motor task or challenging task. um, okay, so these videos are also not working. So this yellow cartoon, what it shows is we are very interested in human balance. So there is a person walking on treadmill, we push them using a cable driven robot, and then we study how the human regained the balance. So it would have been fun if the video was running, so the person is walking and suddenly there is a push and the person recover. Then there is a dancer. So we like to study how these pro movements are being conducted. So this is a Bharatanatyam dancer performing some rasas in the lab. So using this, we create these wearable sensors. So this is one sensor that we have created. It's nothing but just an IMU. What we have actually done is coded with understanding of human signature. So we recorded lot of data and understood how ankle is being used by human, and the idea was to generate these human gait characterization. So when I'm standing, walking upstairs, downstairs, and all that. In today's time, we say, okay, put couple of sensors and we will be able to use couple of ML algorithm and go about it. I mean, that's possible, but inherently there is a very interesting way human use this ankle. So using just the single axis of the gyroscope, we're able to distinguish between all of this. Now, why this sensor become important? It can be just given to like I'm wearing this wristwatch, I can get a little bit more accurate data from that sensor. I can give it to my grandparents. I can give it to PD patients so we can collect that data. Or later I will show this becomes a little bit of a high brain to the exosuits that we are developing. Because what we need to do in exosuits is we need to know what the human is doing. So how do we generate those forces and act on it? So this is how the final setup looks like. But again, in today's time, a lot of students are not interested, so we have to go all fancy. So we have also given AI driven chance, let's make it hybrid, and let's lot of fun. So a lot of student comes in, our purpose is done, new models comes out, we create hybrid. And but yeah, I think this is all fun apart, but this is also important. The analytical model was able to judge only the stairs. It was not able to distinguish between stairs and slope. With the addition of AI, we were able to now do that as well. So I think it is always a better. I think this is right now what the sensor related aspect going on. The second thing I like to share is about human balance. Actually, it's very critical. So imagine yourself walking on the street, but you were busy looking at the chat message or something we all do on Instagram these days, whoever has account, and suddenly there is a perturbation in front of me. What I do? I stumble. If I am good in my control, I will not fall. But if unfortunately my parents are walking, they may fall. They can get stuck and create problem. So typically we might notice that elderly people typically have a conservative way of walking, and then how do we recreate these situations? So dual motor task, dual cognitive task, and so on and so forth. So we are working on it, and VR provides a very nice platform where we can create these lab related and overground and treadmill related situations. There are a couple of other videos we are not showing, but what it can be done is when the person is walking, we can throw bricks in front of you. Now these bricks can change colors. Now you can be asked, if that color is there, you step on it. If the color is different, you avoid those bricks. So it can add cognitive and motor challenges. So kind of a situation like you carrying a coffee mug in your hand and walking through the street. Those kind of challenges, how elderly will respond to it, how adults do it, and how can we utilize this as a gaming exercise for training purpose. So what you see in this second video is a person playing a uh, uh, on a bullseye. He is supposed to get some high score. So that's an activity they are doing. So this inherently gives them a training paradigm. So with this, I shift a little bit going further to the exosuits. The kind of things that we are developing is we record human motion, we understand it. Now the next step is to either assist or enhance the movements that we perform. So exosuits or exoskeletons are of various kinds. And non-impaired person can be using. So, for example, for recreational activity or soldiers or a person working in an industrial setup who needs to undergo a lot of training or heavy weight. Just for everybody's information, these days in European Union, some of these exosuits are made mandatory on the shop floor. So if a human is there, they're supposed to wear some braces. And it's not a new practice. I think if any one of you have tried skiing or for that matter skating, so we wear a different kind of shoe. The reason we do is to just, if you imagine what it is doing, it is constraining your ankle. So you're killing some of the degrees of freedom at your ankle joint. Otherwise, you will fall or you will bend your ankle in a wrong way. So that's a same kind of strategy that is an exosuit is doing. But when it is being used for healthy individual, you can consider that as enhancement. When it is used with patients like a spinal cord injury patient or a stroke patient or an elderly who have problem with balance, they can thought of as a restoration purpose. Now, there are various forms right now that are available. You can check out, there is a website called Exoskeleton Report. Each and every different form is coming out. The idea is to use them for the restoration purpose. I already showed you this video. CP is just one of such neurological insult that we suffer with stroke, spinal cord injury. There are numerous other because of which our society needs assistance. Then our soldiers, a lot of workers needs to carry heavy weight every day-to-day life. Uh, I'm not carrying a lot of weight, but I think when I had two kids, I had to lift them. Then I realized that most of the time when I bend to lift my 3-year-old is in a wrong posture and I end up hurting my back, right? Now imagine a person who is lifting these weights every day, right? So there is a proper posture. How people make sure that you get into proper posture if you are not used to is through these braces. Sometimes we can do it. So using this idea, a lot of other people in the community are also working on it. We have been working on this back exosuit. So it looks a little bulky and kind of, because it's an emulator. So you can change the moment arm, you can work around. We are conducting a lot of experiments. So the idea is, if I have to lift some weight and walk with it, or maybe do certain asymmetric exercises or movements, what kind of condition this suit should be put in. So this is the momentum. This can move upward, downward. It essentially engages your shoulders and thigh. There is a cable which has inelastic and elastic component. So there are a lot of variables. Now you can actually literally optimize for a particular movement what should be the stiffness that your elastic part should have. So it begin with a little curious experiment. So now this emulator is working out, where we are conducting a lot of studies. How does this exosuit affect the fatigue? Right now we just concluded one study, and it's a very interesting how this stiffness to the compressive force that comes onto my back versus the joint torque assistance that we are able to provide. That's a very interesting. Now, again, it gives us the platform to play around. So right now, what we are trying to do, it's still unpublished work. So what we are trying to do is we are creating some mechanism over there where we are trying to remove some of the problems with the passive stuff. Moving forward, so there is this idea of cable-driven ankle actuation that we wanted to do. So we have created this cable-driven exosuit. Right now, the form it shows is that you have to carry a backpack, and it's okay. So there is a backpack of a couple of kilograms that you have to wear and then walk with it. Now, what essentially it has a couple of cables that are going around your shoes, and which basically, when pulled, can assist you around the ankle region. Now, there are a number of sensors, load cell, encoders, IMUs that are there that can be processed together. So this is what the high level part that I was talking about, that we need to know what the person is doing. If I'm climbing upstairs versus climbing downstairs, the force that exosuit needs to apply should be different. Otherwise, it can make me fall. So this is where these sensors become useful. But then, what sort of controller you will use? If you use a position control, you can actually make the person uncomfortable. So here what we are trying to use is a combination of feedback feed forward, where the feedback becomes an admittance control, and uh, using. So it appears that I'm running out of time, so I will just skip few slides and show the video. So this is a couple of years old video. Right now we have been trying to work a little sleeker design of this, because it does appear a little cumbersome, where the person is walking in real time. The sensors sense what the human is doing, the force are getting adjusted, and the system is essentially applying those forces. So it essentially appears that the person is getting a support from the ground that way. So we are currently working on an alternate version, because as Professor Sen in the morning said, it is very heavy. So we need to, the system, if it needs to assist, it needs to be transparent. So we are trying to reduce through some mechanical, different kind of mechanism that we are creating. Um, just to close my talk in few minutes. So another level of work that we are doing is mimicking human musculoskeletal mechanics, um, understanding that through a cable driven system serial chain kind of approach, where we try to generate what kind of joint torque and how human would plan for it, because human legs and arms are redundantly actuated, as well as the degrees of freedom at the joint levels are much more than I need from the task space point of view. And then we also use some open sim myosuit related musculoskeletal simulators to create these understanding. Those understanding in simulator cannot be justified unless we test them. So this is the lab setup that we have built, where whatever we are trying in those simulation, we try to test it before we can come up with that. So with this, I think I will like to end here by saying that the human-centric approach that I'm trying to follow is where we incorporate human neuromechanics and motor control along with the robot physics. So even though we are not literally changing how robots are actuated, we are creating different configuration where robots could be more useful to individual, such that instead of generating a compensatory behavior from the human, just like when a backpack is added on your back, there is an adaptation and internal model development that happens. So with this, I end my presentation, and thank you all. And if there are any questions.
Thank you very much for the wonderful talk. We can take a couple of questions.
Said analytical models cannot distinguish from stairs to a ramp, whereas AI models can you elaborate how that is so?
Yeah. So the analytical model at that point was very specific. We didn't incorporate the dynamics of it. So we only um, recorded ankle kinematics and how ankle kinematics undergoes these different changes. So when you walk on stairs versus when you go on slope. So the signature of human ankle, plantar flexion, dorsiflexion is very similar. So because of the slope, I think you step the same way. So if we created a data driven strategy which was not able to distinguish, I think, how that peak is coming and all that. But when we use AI without knowing, and I think so it was able to create the distinction between the slope
Okay.
versus the.
But you can bring that back to the analytical model if you understand that.
So right now that's what we are trying to. We are creating a hybrid model, but using that understanding, we have not yet thought how to incorporate that in the analytical modeling. But maybe I think if there is a way, we will love to further try that out. Yeah, yeah.
Thank you.
I have a question. Thank you for this nice presentation. So it's not a question, it's a comment actually. So in reality, the contact between all the human joints, they are not perfect revolute joints. We have contact between bones and the surfaces are themselves complicated. We did some experiments comparing conventional revolute joints versus four-bar mechanisms, which more closely represent the bone surfaces, the contact between bone surfaces. We found that uh, when we use four-bar mechanisms, we are able to reproduce the coactivation behavior and also have enhanced range of motion. So maybe this could be an addition in your
Completely agree with you. I think, yeah. So again, we have not. dig deeper into how actual joints of human behave. But when you use rigid exoskeleton, that becomes a big challenge, because then you make a assumption like that there is a revolute joint. But yeah, I think love to discuss further.
Thank you. Very nice presentation. So I was just wondering, like human has many muscles and very complicated motion. So what kind of motor, like you need many motors and many actuators. So how do you manage that?
I mean, so we are ourselves struggling with it. So the motors that we are right now using, um, they are decided right now based on the speed and the torque limitation. Um, Once they provide that torque and speed, then we create our own mechanism. So that transmission is through, let's say, a clutch-based pulley mechanism that we create. So that is what we are trying to develop in our lab. But motors are some electromechanical motors that we just buy from the vendors.
And you need many, like you just can't have one or two, right?
So yeah, so
Many
again,
people.
because we are also going redundant, so you have more, and that creates the problem of being heavy and bulky. So we don't have a proper solution to that unless we actually dive into creating different version of actuators. Yeah, it's a problem for us. Thank you for
Thank you.
highlighting.
One last question from
Yeah, very nice talk, actually. I was just wondering whether you have explored usage of compliant linkages, or compliant joints in your any of your systems. Can you elaborate on that?
So not yet. So all of this cable-driven work, we have not yet dive into that part. But there is some inspiration that is coming in. So I will love to explore those further. So, but so far we have not yet.
Thank you. Thank you very much for the very interactive question and answers. I would like to request Professor Rajiv Lochan to present a memento to Dr. Vineet Vashishta. Thank you, Professor Vashishta, for this interesting talk.
Thank you. Thank you. Thanks, Rajiv.
It's time for our second invited talk of the morning. I would like to invite Dr. Kiran Akella onto the stage. Dr. Kiran Akella is a scientist G and project director for systems and technologies for advanced robotics at DRDO. Earlier, he headed the Computational Mechanics Center. With about 25 years of experience, his work spans computational mechanics simulations, composite structures for defense applications, and in recent years, the development of legged robots. His research interests include dynamics, nonlinear finite element modeling, biomimetics, and leg locomotion. He holds a PhD from IISc Bangalore, an MTech from IIT Kanpur, and a BE from VNIT Nagpur. Dr. Akella has authored more than 30 publications in national and international journals, holds 3 patents and a book chapter, and has guided 2 PhD students. His recognitions include DRDO Young Scientist Award, Lab Level Scientist of the Year Award, and the Defense Technology Spin-off Award. Dr. Akella, thank you for joining us. Stage is yours.
Thank you for the introduction. It's a pleasure to be in IT Hyderabad campus for the first time. I think I came in quite late yesterday, but I still could feel that it's a very well built campus. I'll maybe take a walk today evening. So I come from uh, a lab in the western side of India in Pune, which is called Research and Development Establishment Engineers. A strange name because of our origins with Corps of Engineers, starting from the Corps of Engineers of the Indian Army. And so it has this bracket, engineers. So we are engineers too. And then we work on a different range of systems. The field defense, where protection, a lot of bridges, mine warfare, some tactical launchers, military robotics is one of the main areas that we are working on right now, and some airborne and strategic systems. So, of all the robots that we build, what we are proud of in the most recent past is this unexploded ordnance handling robot. Whenever we have some sort of a sensitive situation, this robot comes into action. There are a lot of these 1,000-pounder or the 500 kg bombs which are dropped, and this robot goes. It has a water jet cutter. It has a 7 degree of freedom robotic arm, which operates this, cuts the explosive, takes it to a safe distance, and burns it. It's been used extensively by the army, and we had a lot of air force primarily. This have to use this on the border, and then this is another robot that is there for handling various explosives. So with this background on robotics, we come to our the project that we are working on right now, which is called STAR, Systems and Technologies for Advanced Robotics, in which we are three DRDO labs are working together. Uh, is this okay? Yeah. Three DRDO labs are working together. One is ourselves, and then there a Hyderabad-based lab and a Bangalore-based lab called CARE. So this project aims to work on different technologies. It's a large project spread across a period of 7 years. Surveillance and perception to perceive the environment, give the situational awareness, work on autonomous navigation, especially in unstructured terrain, the kind of terrain that our soldiers face in the border. Collaborative dual manipulations, once the robot goes in this terrain, it has to do certain things. So dual manipulation, and then support in combat whatever way it can. In addition to that, the target of this project is leg locomotion, where we are looking at multiple ways to negotiate terrains that we face in the front. So we are building two systems, a quadruped and a humanoid, to do these activities and replace the soldier in various hazardous activities that he does. This is the first biped that we have built in our lab. You can see it. So this is where we call it our two-leg locomotion test bench, where we are working on different aspects of how to make how to start of doing the balance and control and all that together. So you can see this. Now the first thing that when you come to building such robots is the actuators. The actuators, there are a range of choice of actuators that you can choose from. Typically the two main that are there in the people you building these kind of systems use is a multi-stage planetary gear or a harmonic gear. So we have, in this entire process of building this robot, chosen the harmonic and the motor kind of based system. Now this we found was the most compact at matching gear ratios. For given a gear ratio, it was the most compact. So we use these strain wave gears, and on the side of complexity and cost, harmonic gears are surely far more expensive than multi-stage planetary gears. But we have certain benefits of compactness. You can put so many actuators together, and the design choices that we have is we can have for the ranges of torques and responses that we want. We were able to use this to the best. So that was the reason. And then we have these multi-stage planetary gear boxes which are being used in different robots. The drones, people use it a lot. The problem with them was for a matching torque, we have we for the matching torque, the the current drawn by these robots is the motors is much higher, because you need a much powerful robot, a much powerful motor to drive the same if you have a smaller gear ratio box. So with that, the current drawn by these motors is much higher. So a robot has to have a, instead of a 48-volt circuit, it has to have a 60-volt or that kind of circuit. So that's where we found the harmonic drive to be much better. And speed, of course, the planetary gears box gives us a better, higher RPM for the same motor weight and size and torque. So that's the benefit that we get, but we get far other benefits in terms of efficiency and responsive. Both these motors are same and similar, and back drivability and backlash is tougher to achieve backlash free in planetary gears. It's easier in harmonic. Back drivability also for the same gear ratios. If you look at gear harmonic drives, I can go to much higher gear ratios, but for the same gear ratios, I get good back drivability and backlash. Now, how we assemble these actuators? So we decided to build our own actuators, in the sense that though the components could be bought sourced from outside, you have to build these actuators yourself. These actuators consist of multiple components. So they are frameless motors. So these motors comes in component sets. You have the rotor and the stator separately. You have to mount them on in an enclosure. Then you get these component sets of these individual harmonic drives or the gear sets. You have to have two encoders to take care of the incremental and the absolute encoder. The torque sensors and brakes, right now we have not included them in our robot, mainly to, you have to make it simple but not simpler. So as it is said, so we try to remove them and have a more compact robot. The biggest challenge here is building these actuators is your component and assembly tolerances. The tolerance, you get these tolerances, the harmonic drive, these motors have a certain tolerances. And when you assemble this entire actuator together to function as a single unit, the assembly tolerances and all this have to be worked out in great detail. And we learned that the hard way. You need a lot of assembly fixtures, you need a lot of things. And then finally the thermal management, the fins and the kind of adhesives you use to bond the motor with the enclosure. You need conductive adhesives, you need to do so many things. So at that level you need to do a lot of engineering at the small scale to build these actuators. And the advantage is, of course, you can choose different sets and build the kind of actuator you want, but the pitfalls is that you have to go through all these steps and to be able to build a good actuator which can do something useful. Look, there are almost about 30-40 parts, precision machine parts, which go inside each of these actuators, and they are very complex to assemble. Just to show you a simple actuator schematic. So this is the actuator that we have, one of the actuators in the hip of the humanoid. Now you have to, this is the side which gives the motion, but you have to have an encoder that side. So but you cannot put there on the motion side, so you have to take a shaft through this hollow shaft, keep that encoder here. This is the incremental encoder on the motor side, and this is the second encoder on the load side. So you have to have this kind of very complex precision machine parts within the actuator to be able to build that. So this is the harmonic gearbox, and then you have the motor here. So all this together has to be has to work as a single unit, and that was one of the biggest challenges that we faced while building this. The knee joint, again another complex thing. We were talking about exoskeletons, but when you even, I mean, exoskeleton looks like a far higher problem than when you look at this, but this itself is very tough to engineer, in the sense that just achieving the actual knee motion. So you have this roller screw, the screw mechanism with a motor here, which moves this knee up and down, and again this actuator has to be built like taking the motor, the encoders and all this together, and a roller screw here. The ankle is another very complex mechanism. We were looking at how multiple muscles work here, and you have to make them work in coordination. So how this chain of motors work together and give you this kind of motion of roll and pitch that you call in the classical terms of the ankle, with motors kept high above, so that you can achieve a lightweight leg base. So this complexity of the mechanism, there's again you have to make a lot of choices, engineering choices here. One choice that you come across is whether you have to use a roller screw or a ball screw. A ball screw is simpler, is less friction, but it is much heavy. It is heavier. So roller screws are much more compact. So we all these mechanisms we have primarily used roller screws. They are lighter, though they are more expensive and precise to make, but we have to use them. Just to tell you this slide I have kept to show you the complexity of the transmission for the ankle. So the ankle is controlled by two motors here in what you see at this location here. Then it goes through a belt drive. This belt drive operates a gear, two gears here, and those gears then run this ankle here. When the motors run in sync, so Professor Vashisht was talking about collaboration between muscles. Here the motors have to collaborate. So when the motors run in sync, the ankle goes like this, and when the motors run in the opposite direction, the ankle rolls. So this series of mechanisms you have to build and make it work real time when you do the balance and control. Just a simple feature like the shaft that's there at the ankle, the kind of shaft you have to have measurements at these two locations, how much it pitches. So you need encoders to be mounted here. So you need a very complex, this kind of shaft here that you can see at the base of the ankle. So this, it has to rotate in two directions, and building this and making this function together is quite challenging. The next part is after the biped, we we have we, we typically face situations where you have some very hazardous object to handle inside a civilian area or some such areas, and you have to deploy these robots. So one of them is it should have a very dexterous manipulation. Our robots today are very the available are very sort of rigid structures which go and which cannot dexterously manipulate. They have a single arm. They need a lot of vision things, feedback from the cameras and all that. So uh, we are trying to develop this as a product which can do these hazardous tasks separately. And the we build some test benches. Now here we have the advantage of using what we call test benches, in which we take standard commercial arms and mount them in a horizontal way like this on a torso, and use those arms to study the various manipulation algorithms while we build our own arm, which is much lighter and capable to fit on a humanoid. So the arm assembly is similar to this entire leg assembly is complex. Each has a different set of challenges. The way we assemble the encoders, the way we give these joints, and how to optimize the weight of each of these open cage designs so that you get a much lighter arm. Today, arm which picks about 5 kg payload at half a meter or about 0.75 meters weighs about 25 to 30 kg. On a humanoid, you cannot put those kind of heavy arms. You need to be 7 kg arm or 6 kg arm. So that's why you need to work on all these arms, and we need dexterous arms. Finally, we need a robot which does something useful when it goes there, because otherwise the armed forces will not, or the people working in the defense will not like it. So we have to build a usable arm with the challenges of the weight constraints that it offers. Again, similar actuator and joint configuration details. You have to, there we struggled a bit with in assembling the encoders. So here we were slightly smarter. We used pre-assembled harmonic gears, and then the motors were there, and then we built these encoders. This system is getting built right now. The third thing is what we are working is the quadruped. The quadruped, again, from the army perspective, they ask for a simple thing. They say it has to carry weights and go up the mountain. So we have our borders which have huge, which have a big area covered by mountains, and what we need is we need today a lot of mules are being used by the army to take stuff up, to take to things in these areas. Uh, so these robots are supposed to reply. So again, the choice of actuators is important here. That it has to be scalable. We cannot use a design or an actuator concept which is not scalable. So Again, we chose this kind of motors with the motors and quadrupeds with harmonic frameless motor and harmonic drive. Basically, it gives us scalability. Uh, Different leg configurations and mechanisms that you can choose from. There is a chain drive, there is a 4-bar linkage, there is hydraulic quadruped, and all this combined, we looked at all of that and chose whether it should be this kind of M configuration or an X configuration, whether you have to use. So based on certain decisions that we thought best at that time, that we can have shock absorption, so we used a belt drive rather than a chain drive. We were building our first prototype, so we needed flexibility to change many things. So we use this kind of arrangement here without a 4-bar linkage, because every time we change the configuration, the linkages have to be changed. So this, with considering all this, we chose this design. Again, you have to build all this these actuators. Here we used, just to make it simple, we used ready-made motors and with harmonic drives integrated, but this complex mechanism which runs the ankle and the knee are separate. And the challenge is in system integration. Each of these robots come with a very strong system integration challenge. If you just assemble them, they would look something like this. So the cables, the EMI issues, you have to use sniffers and find out why this is happening. The power cables, you cannot really separate the power cable and the signal cable very well. They are all so closely packed. Here you have to control 12 motors. You have to put those, that IMU. You have to have the foot sensors. Everything comes together. The batteries, everything comes together in this small package. So system integration is space management. System integration is big challenge there. Another important aspect is the gripper. Finally, what interacts with the objects is the gripper. There are multiple design choices to be made, to be taken here. While you design the gripper, there is, of the two commercially available grippers, is this is the under actuated mechanism of the robot IQ, and this is the multi motor of Tesla. So these two grippers, we are using this in our initial prototypes, but the one we are building, we have explored 3 designs. One is a modified version of this with at much lower weight. This The second is where we given the fingers a swiveling mechanism so that you can rotate and hold complex objects. And the third is more using screws, linear actuators, and operating these fingers, where we are getting far more dexterity in operating different things, different shapes of objects. So that was, we did a lot of work on this, developing our grippers, and we are going ahead with a design similar to this right now, and we are exploring other designs. So this, again, I'll not go more into the scheme, the control schemes and all, but balance and control, all these schemes are very challenging, and we are doing a lot of work towards this. This entire robots have to be tied up in an electronics architecture, a hardware architecture, which is sort of scalable, which takes all these sensors, which processes data real time, and you have to take these decisions at the beginning, because later you'll have you have build a system which cannot function. So we chose the fastest interconnect that works between the robots, the processors, the choice of processors, how you have the motor controllers, and how this entire thing functions. We have a common hardware architecture across our systems, which we had planned before. Computational platforms, as you know, AI and all this, the audio perception, visual perception happens inside in fact, our robot brain is here. so the brain is here, and the brain needs all this computational loads to be handled in a very compact factor. So we have an expertise of building onboard computers for aircrafts and all other systems. So the team that is doing this is building an onboard computer for us, which has all the necessary cards and all sensor interfaces and things like that. Power, again, one of the most important challenges is power. You have to manage power. You need 5 volt to 48 volt in the motor to 5 volt, and all that comes from a source. And once these motors are operating, you cannot have reduction in voltage, you cannot have all this, and still you cannot carry a lot of weight of battery. So this puts a constraint on the power management. There are some algorithms which run only for the power management, so that is itself challenging. Sensors, right now we are not developing any other than one or two. We are not developing any sensors. We are using what are commercially available, and some of the work that we are doing in terms of videos. So this is dual arm manipulation of operating different things. So this is the gripper, this is the test bench we have, and this, so we are doing things with collaboratively with that one arm is aware of the other. This is actually not using any vision. It is doing this entire thing blindly by closed loop IK. So one arm is the aware of the other arm. So we are giving one arm awareness of the other arm through just through IK, what we call closed loop inverse kinematics. In fact, we are publishing this work. So this both the arms are correcting their position by just by using the IK and then trying to do this task of loading something inside something or handling this. The null space control is where when you have this glass of water, a fragile object, and then you are moving the elbow while maintaining the orientation and of this. So using the 7 degree of freedom arm. So this all these algorithms we are working on right now, and handling fragile objects like eggs without by compliance control. This is another thing that we have been able to achieve. Using vision, uh, the closed loop IK, we have repeatability and we do things in a very short while. But once the vision and this entire pipeline of grasp planning comes, today it takes just to do a simple task like bottle opening, it takes 3 to 10 minutes. So that is the situation that we have. We need to speed this up, and there are huge challenges on how this computers work, how these algorithms work, and how we make them fast, do things faster. These are all highly 3 times, 4 times videos have been made to run faster. This is a bottle opening task, a very complex task of this similar to handling an explosive or something like that. Very complex task of identifying one angle and doing the other things. Typical task like door opening. This robot has to go inside buildings, and if it has to look at then door opening, and then handling two stuff, handling thin objects. So this uses vision here and is operating this. So the biped is, we are still struggling to make it walk. So hopefully it will start walking soon. We just build this system and we are working on it. The responsiveness of the actuators, we call it. It's more on the surgery bed, getting repaired and built rather than doing walking. So we keep correcting things. We keep doing things, and every now and then it goes on the. Right now it's on the operation table. So every time we have to fix this. So and we'll do a lot of this algorithms and control on smaller robots. Just this simple zero movement point control, we study them on these smaller robots, and as a simple mechanics based control with just 3-4 lines of equation, you can do these kind of things. Once this robot, we stripped off this code of the biped and wrote this control law which uses the ankle control in now. We just remove all the software and put our own and make this run. The quadruped, of course, with this build, we have done a lot of work on how to on making this quadruped go different places. We are also doing something on RL. Until now, though we get benefits with this entire AI approaches, but things like autonomous navigation and all, we tried multiple approaches. One is the classical image recognition, cost map generation and all that, and other is the RL based approach. Whether it's our technique or our lack of uh, our this, we never found RL to outperform the classical approach. What we felt was the classical approach with some places of added RL here and there, or this entire AI things helped us far more than having a end-to-end RL based approach. The thing, it work faster, and this quadruped with this is the commercial available quadruped using vision, jumping and identifying these things and all. quite a lot of these things are classical methods with some places, some RL here. This is stair climbing and completely blind locomotion on it when it hits with sensors and using. We are doing a lot of work with collaborations with different people. We have different kinds of work is being pursued at different universities across the country for this project. The whole body dynamics, walking on soft terrain with IIT Kanpur, closed loop gripping using using tactile sensors, how what happens when there is no tactile sensing and what happens when we have a closed loop gripping, point cloud generation from a rough point cloud to a more finer point cloud, collaboration between two quadrupeds and working on different actuators. This is another academic program. We are also building like an artificial skin or a set of tactile sensors. This is a 15 by 15 sensor which is on the fingertips and on different places which we have built to to for the closed loop gripping. Energy is one of the very important aspects here. So we are working on uh, the using endurance. See, today the robots have endurance of half an hour. This is the time of endurance we are talking about, and we cannot. They are not fieldable. We need 5 hours endurance, 4 hours endurance with ability to do work at that load. So we are looking at multiple solutions. One of them is a fuel cell. With the same weight, we believe that the endurance can substantially go up. We're also exploring, in addition to the academic collaborations, we are looking at this building our encoders to a India through a what we call TDF, Technology Development Fund, where we fund an industry to do this. So we have a lot of collaborations ongoing in this. The future directions are that we need to make a long way ahead. Viksit Bharat, we have a roadmap. So first is build some of these and then collaborative approaches and then managing. A lot of technology challenges that we have to go closer to the realistic robots. Um, what the army guys see is videos like this and they think that the robots can do anything. What happens in reality when we build when we field the robot to the army is something like this. Okay, they see those videos and they say this, can this robot climb that hill and come back on its own? So we say no. So they once they get into the field they get this kind of feeling, the reality, and simple tasks like coming out of a car or moving constant. This takes such a long time. When we were doing that bottle opening task, when we perfected it, it took us 10 minutes. Now we have brought it to 5 just to do a bottle opening. So this is the situation today. So there is a huge, this was the DARPA Robotics Challenge 2015, and this is a very recent video of how this manipulation occurs of really large and heavy objects. And it's still there is this robotic motion and there's a lot of work to do to make it more usable and do things with which things like that. So what people imagine is a robots like this, but where we are is somewhere here. There's a significant gap between technology and expectations. There's a huge thing to go so that we can give this robot to the users or to the services and say use it, it will climb up the hill and do things, carry weights for you. Far away from that. That's what I just wanted to. And we are trying to build this ecosystem to to develop these robots and to work in difficult environment, unstructured terrain. When we say our robots work in fair weather, it needs light, clear light to do navigation. And they say most of our operations are done in pitch darkness, complete foggy environment, the worst possible weather. So I say our robots cannot function there. We need bright weather and sunshine and all that, and only then the robots will function. So that is the situation today. We have to go way ahead. Thank you.
Thank you, Dr. Akila, for that wonderful talk. We can take a couple of questions. There.
Hello. Thank you, sir, for the fantastic talk and introducing a lot of fascinating technologies for the future and letting us know the the current trend actually that we realize where we are. I'm just wondering, when you are developing that quadruple, so how much the payload it can carry, and what the expectation from the army side?
Yeah.
Because as you mentioned, they want, I think maybe 500 kg.
Now 500 kg is a little too much, but what they are looking at is the first thing is replacing the mules that they are using on the border. They spend a lot of money on mules and training and doing a lot of things with that. There's a separate regiment which works on that. So to carry these weights on those areas without being sort of seen and observed and things like that. So that is replacement. So typical in a mountain area, 50 kgs is what they are looking at. Okay, and 50 kg with the ability to climb, go up with carrying the payload on that thing 50 kgs. So we were not building those payload robots right now, but what we are trying to build the basic blocks so that you can scale your design up something. If you choose your actuator and your things such that you can using a bigger motor and a bigger gearbox and things like that, you can build those motors, or hydraulics. Using hydraulics we can carry heavier weights. So we are working on all those building blocks, and once we are sure of them functioning together, we can then assemble it as a project and give it to it. So that's our direction.
Yeah, and other connecting question. So as you mentioned, endurance time. So I mean, I'm just wondering where we are actually in terms of quadruple.
So it see there's a lot of this literature which says 2 hours endurance. That's the maximum you can get, but that's for very simple walking and things like that. The moment it starts climbing up the hill and stairs, the best we found out we could get is about 30 minutes to 20 minutes. So which is not good enough for doing anything. So we need to increase endurance. How to
Yes.
do that is 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 an unknown question, but an
Thank you.
unanswered question yet.
Yes.
Um, Sir, just a few slides back, you were talking about one of the collaborative projects you are doing currently, which is on battery life.
Yeah, yeah,
Basically, we currently only have like half our viability.
yeah.
So, typically, if you need robots out in the field, you at least need a 24-hour viability for.
Yes, yes,
But you
yes.
are talking about like 5-6 hours.
Yes, yes. So what the statement made about this is that these robots will remain intellectual curiosities in the lab unless they solve this problem of endurance. So they have to have high endurance, and there doesn't seem to be a simple way out of this problem. We are
Uh,
not working on those foundational technologies which help increase endurance. Somebody gives us a better battery or better power supply, we'll use it. At our center, we are not working on the found, but there are many people
what
working
I
on
was
this.
going to say is,
Yes.
typically we use lithium ion or those
Yes,
kinds. Can
yes,
we switch to like using supercapacitor like
yes. So, but these are not revolutionary. Supercapacitors will help you deal with those spikes.
yes.
Okay, we use lithium ion batteries with some supercapacitors to deal with spike. You can deal with spikes in a different way. You can have an extra battery to just for the spikes. You can do so many other things in power management. But that will give you 20% benefit, a 10% benefit. It
That
won't.
also will work. Even
Yeah,
for
yeah.
any practical situation also, even
Yes,
5% advantage is quite big.
yes. So that.
So I hadn't fully completed my question.
Yeah.
What I was trying to say is, if you use any kind of battery in order to prolong life, you're talking about more weight into the
Yes,
system.
yes, yes,
So the battery is central, right? It
yes,
connects to every motor, everything.
yes,
But is it possible that instead we can just split it up and get
yes,
complete decentralized system?
yes. So that's what we are doing in the humanoid. At least that's the goal that we have. We are looking at flexible batteries. We are looking at decentralizing this power, putting some batteries here. So this kind of strategy is done in aircrafts for fuel and things like that. So we are trying to do that. We are building these even in the quadruped. We are building 4 batteries to sit in all these small corners that are there
Means
in each
it's
place.
basically like a charging is happening at a central core.
Yes,
It distributes a bit of the power to any
yes,
of the companion batteries. This
yes.
way, when a robot is basically is it possible to create this ecosystem so that
Yes, yes, yes.
we are not
It's possible. That's what I'm saying. It's used in a lot of systems today. Most of these systems don't have one single battery which does all the work. So even in you look at aircrafts or other places, they're distributed in multiple areas for weight.
Thank you, Dr. Akila. Thank you for the Q&A and the wonderful presentation. Uh, I would like to invite Professor Matthias to present a token of appreciation to Dr. Akela from the organizing committee side. Thank you, everyone. Now we will move to the seminar rooms 1 and 4 for our technical session of the day. And then we will have a tea break and come back here for the memorial talk.
मिलिए आप लोग टी टैंक से ये पटरियों पर चलता हुआ एक असली किला
voice is simply faster, more natural, and more flexible than typing. He said he has a voice pill, and I can see why.
It is my pleasure to introduce this year's Professor K. Lakshminarayan Memorial Lecture speaker, Professor Dibakar Sain. Please give a round of applause to our speaker. Professor Sain is a professor of Department of Design and Manufacturing and of Mechanical Engineering in IISc Bangalore, where he joined as a faculty in 1998. His research interests include digital human modeling, mechanical assembly analysis, AI and VR for creative design, kinematics of mechanisms, and so on. His research received funding support from various labs and organizations such as DST, ADA, ISRO, DRDL, Boeing, Wellcome Trust, etc. He has developed several novel products, predominantly in the domains of agriculture and assistive technologies, which has led to the formation of few startups, such as Sickle Innovations, serving small farmers, and Grasp Bionics, specializing in smart upper limb prosthesis. He has over 100 publications in international journals and conferences. He holds 8 Indian patents, and 8 more are on the way. Professor Sain, the stage is yours.
Uh, Good afternoon, and thank you for these organizers for giving me this opportunity and honor of presenting the K. Lakshminarayan Memorial Lecture. I know very little about Professor Lakshminarayan because I did not have direct interaction, but his encountering his work became sort of inevitable uh, due to a very innocent question that I posed to myself many years back that will come, although I'll come to that. But how this whole topic started is that why it is so easy for uh, assembling things as a game, but it is so difficult to do the same thing in a computer. Maybe we are missing out something very intuitive in our structuring of the knowledge that is required for uh, handling things in computer. By the way, I do most of the things in computer. That's why I want to convert everything into a the computational framework. All the things that I mentioned as my research interest can be packaged into two words, which I say shape and motion, and they're independently as well their interaction. Understanding shape, understanding motion, understanding relationship between shape and motion. So this whole topic therefore encapsulates the meaning of my research interest, but applied to a certain particular situation which leads to interaction between shapes and kinematics. But I sort of tried to use this word kinemagics as an explanation to that. Many things we take for granted, right? And trying to understanding the inner working such that the magic is revealed. Okay, so that my whole endeavor here, and out of the whole field of kinematics and mechanisms, this whole talk will cover only one very fundamental aspect, which is how to understand the interaction between two shapes, which nothing but is called a pair, right? When two things come and interact with each other, that is called a pair, whether it is a human being or inanimate rigid bodies, right? Pair is the same, and hence they put constraint on each other, they allow certain kind of freedom. Okay, so that becomes our useful thing. So shape, contact, and kinematics or kinemagic, and this is the one slide on Professor K. Lakshminarayana, and yeah, uh, this is the work I was referring to. But you notice that this is what's a very widely referenced paper, kinematics of form closure. However, his original publication is not accessible, right? I tried many different ways, and this was what I could get access to also due to get independently as well as from Professor Ananta Suresh, who forwarded me that. Yeah. So this is one of the work that we could refer, and it is in some sense, in as we progress, you'll see that why it is so much widely referred. Yeah, how the thought process is quite different. Now, the term form closure, right? It seems that uh, it requires certain kind of understanding about that, what it means, right? And if you see, to quote from it is, right, first is why down form has been predominantly quite downplayed in mechanisms, right? When you study mechanism studies, we hardly talk about form of things. Rather, we say that link is a rigid body and pair is a the pair of links under mutual constraints of motion and blah blah, right? And whole thing becomes very abstract. And then we say that link geometry, okay, there is a whole plane is my conceptual link, so it becomes abstract. And whatever form that we have in the real systems, we ignore that and convert it to something like this. And why you do that? And whole thing that is there like that, that also, which is a physical embodiment of a maybe multiple joint, and then we simplify it just like a small circle, like a dot. Okay, this level of abstraction is done. Okay, now this is the kinematic abstraction. If I have various forms of links, finally it is represented like a plane figure like this, and eventually like this. A strip down, how much we are stripping down. Now this is a very conventional what roller bearing, right? Now, is it a, this is widely used in all revolute joints, right? So this is an iconic revolute joint, but is it a revolute joint in the sense that it is two links interacting with each other? Actually, if you see the full detail, it is a hugely, a complicated mechanism in its own right. Yeah. So this abstraction has got some benefits, which says that abstraction removes visual clutter, so analysis becomes somewhat simpler, and it allows us to focus on the essential. That is fine. But what we are missing out? We are missing out the basis of mechanical behavior, which I say function follows form is in mechanical engineering, right? If you get some function, it is because of the form. Whereas in product design, we generally use the word form follows function. Right. What form I use for functional, there's, we have to give priority to the this thing. Okay, so from that point of view, there is a difference, and we have to acknowledge that. And if you see this, our basic uh, framework which we run in this lab is that I say that geometry rules. Right? Other things are consequence. If we understand geometry, we understand other things. So what are the other things? The form governs motion. And this is one which you cannot deny, that the uniform motion in a gear is because of the particular form of the gear to profile. If that profile is not there, we still get motion, like you used to have that cog and cage kind of gears, which is maybe 2000 years back. It was taking water, right, pounding grains, all these things it was doing. But what was missing was that they're slow machines, so these perturbations of the force, the motions was not that significant, or we could not actually understand that. So interaction of the form at the interface of two rigid bodies decides the nature of the relative motion. Therefore, few things are required. Form is required, interface is required, interaction is required, and result is the magic of motion. So if we do not understand these, motion remains a magic, means there is a trick which I don't understand how it is happening. Okay, so this is the last time I'm going to use the word magic. Okay, remaining slides are not having any color. Okay, so now notice that these are the kinematic pairs as a physical entity, and if I understand this, only then I understand this. Now, what is difference is that if I'm provided with this, certain kind of motion is assumed to be available without regard to how it is achieved. Moment we have to design, I need that information. I need this, how to get it is design. I have it, how it behaves is analysis. So this helps us to do analysis, but not design. Okay, and beyond that, we have so many varieties of kinematic pairs that are possible beyond the six, right? Which are derived based on the geometric interaction, which is intuitively we can find out. Okay. Question was that whatever we are looking at a intuitive level, right? is it possible to derive or understand it from more rigorous way? So these are the two different things I'll talk about. Okay, so you see that these are some of the lower kinematic pairs where if you see in textbooks they'll say lower kinematic pair means surface contact, higher kinematic pair means point and line contact, right? So that is actually misleading. We know that these are revolute pair, but there are point contacts, and this is not sphere inside sphere. And if you consider, well, should not use, but its motion is prismatic or cylindrical, but it has got a line contact. Okay, so what is important is relative motion rather than description of kinematic pair in terms of the contacts. So this feature also appears well back when the Relo wrote the book, right? But our motivation was not that understanding the basic, right? The whole work started long back to, as I said, simplify this situation. If you see the CAD packages and creating mechanical assembly, you have to take the part and painstakingly define lot of constraints called mating relationships, axis-axis coincidence, and line-line this thing and all. I wonder, anybody has ever seen the center of a circle? If a circle is provided, anyone can say it is a circle, but do you see a center there? So circle is real, center is mathematical. Similarly, cylinder is real, axis of the cylinder is imaginary, it doesn't exist in real. Therefore, when you are saying that axis-axis coincidence and the cylinder is generated as a nerve surface, right, then axis is not there. That means same cylinder, if you generate as an axis and radius, I can do the assembly, but the same cylinder, if it is generated as a nerve surface in any software, you cannot do the assembly because axis cannot be clicked on. Okay, with that, we started thinking that what is the more fundamental aspect that I need from there, and that will enable me to do some things. On the other side, if you see the multiply dynamics package, you have the link geometry, mass properties, all these things, and you need a kinematic assembly model as a reference, and then you have to give kinematic constraints in terms of some uh, markers and things like that. Markers is nothing but independent specification of some local coordinate frames, and joints and their behavior are imposed by saying that this is the type of relationship between two frames of reference. That means there is no guarantee that the kinematics, the physical shapes that are available and the kinematic constant that I'm specifying are actually compatible. Okay. So what governs the consistency is the respect for the shape. So if I take care of the shape, these are inferences, no specification is required. Okay, and that is what we started with, and we said that this so many problems are there in it. And one interaction with Mitsubishi Heavy Industries from Japan over this thing, they said that this step takes 80% of their time. Okay, so they wanted these frameworks so that they can accelerate the process, right? Well, that did not lead to any beneficial interaction. That is separate issue. But I came to know that these steps in industry takes a lot of time, and that even after actually constructing the assembly. That means two departments, one that considers the product model, other that considers the multiple dynamics, atoms and stuff. The transfer is very, very expensive. So what we wanted to do, reduce the designer's effort in creating kinematic models of assemblies using available details of part geometries. That was our original idea. Inspiration is, if a 2-year-old kid can assemble a Lego kit, why my computer cannot? Okay, why you have to say so many things to that? So idea was that, can you bridge this gap? And the hypothesis is that an in-depth understanding about contact is sufficient to determine both relative part position, which gives rise to mechanical assembly, and motion, which gives rise to multiple dynamics model, simultaneously without the need of explicit specification of assembly or kinematic constraints. Now, this is the hypothesis, and through this work, we wanted not only wanted to validate this, but also show it that it is indeed possible. Right? So problem was figuring out a kinematic. Given any two geometries, I say that this goes here, right? Then can we say what kind of, whether it is possible, or if it is possible, then what kind of kinematic pair it will constitute? Because all the mating relationship in assembly is, it is always concerned two parts at a time. So two parts at a time and a constraint is nothing but a kinematic pair and their constraint. So that is the idea, that how one is in that case how to determine their relative assembled configuration and what relative motion will they have when assembled. In this subsequent slides, I'll focus primarily on this, that if they get assembled, what kind of motion I'll get. So if they get assembled is conditional. It means that can they be assembled, and if they get assembled, then what kind of motion I'll get, right? If I give a peg in a hole and the hole diameter is very big and the peg diameter is very small, you know that is not going to make a cylindrical pair, that will rattle a lot. But in SolidWorks or anything, axis-axis coincidence, it will still make a nice cylindrical pair. So that is, and if the other way around, it will interfere, that is not good. So this part of geometric reality is taken into consideration to decide whether they can be assembled. And what we do is that we first check that, because we have only finite number of lower pairs to consider, which is simpler. I say, okay, if they get assembled, will it make a revolute pair? No. Okay. Will it make a prismatic pair? Will it make a spherical pair? We ask these questions in their respective form, and I get there. And a sort of a footnote, if you like, in this whole paradigm, both what I did and what is available in literature, you'll find that dealing with helical pair analytically or symbolically or rationally is sort of not addressed generally, right? That is a separate issue. If time permits, I can talk with this. So we do not consider helical pair in these things. Apart from that, other types we consider. This can enable simple, what will give me that? It can enable a simple drag and drop method for simultaneous generation of mechanical and kinematic assembly that can be done by anybody in no time, right? You click here, it snaps it, and then it also constructs a local frame of reference and says that this is my marker with these kind of constraints, and goes to the multibody dynamics file. So that up to that was done, but it is not included in this presentation. My presentation will primarily focus on this one. Can we identify that? Okay, so motion of shapes in contact. Three issues has bothered the great minds since long: how to formalize, how to formulate, how to analyze. So from there, if you see, the first thing I'm talking about is Professor Lakshminarayan's paper, which says here that that terms of form closure and force closure are well known in a tribal sense. Okay, I could not find a very nice formal definition of those things, but through these studies, if you see, there's something emerges, and turns out that it can be inferred from some earlier work, which I'll cover. That so, if the contact is self-sufficient in maintaining itself without reference to applied force, we have a form closure. So that is, in some sense, the characterization or definition. Okay, but Relo gives a somewhat more abstract definition. To put the matter differently, if the requisite contact is maintained, whatever be the applied force, maybe we have form closure. So this is the novelty of the work of Professor Lakshminarayana, that he brought in the context of force within the study of form closure. Before that, it was only form and motion. There was no context of force. Therefore, from here, what we take is that he is implying form closure is persistence of contact. What part we are not covering here, which is very critical, and when we try to analyze, is the contact of what? What is maintained? Is it the identity of the point of contact, or the fact that two parts are in contact? Okay, irrespective of whether the points of contacts are changing. Okay, so those things matter when you're formalizing or analyzing these things. This is where the Relo book started, that from pole to, he calls it centroid, right, which presently we call it centroid, right, that taken two rigid positions, and then you define pole, and successive positions we get these contours, and when they become infinitesimal, like P is following this curve and Q is following that curve, and then you can define two curves which are actually rolling over each other to give the motion of the rigid body. So this rolling of two shapes, hand motion, right? That is what is the characteristic of that. And but in his logic or presentation, you'll see that somewhere down the line, this part is sort of gets broken. He tries to join it back somewhat towards the end, but in a very, very passing way. So for example, say, what is the pair of element characterization? That one element we fixed related to the surrounding, and that the element so formed carry upon within itself envelope of the second. Okay. Third one is that must be so arranged as to prevent every motion of the second element except the one which is required. You see that description is fully in terms of shapes and motions. And the constraint pair, he says that while this motion is happening, right, and the stationary element holds the moving one as it were imprisoned, right, preventing every motion except a single one, forcing every point on it when it has begun to move to travel in a determined path on which account such a pair of bodies may be called constraint. Okay, so therefore constraint and a single degree of freedom got connected here. Okay, now this is important. Though not formally presented, that why we have only 6 types will come from this particular statement. So then he says that these forms have certain kind of envelope, and they are indeed reciprocal envelopes like that. You see that these are all intuitive description. There is no derivation. So he deeply understands what is happening. Imagine a case filled with both conditions, and in which at the same time one element not merely forms an envelope the other, but encloses it, in which that is to say that forms the elements are geometrically identical. Okay, these envelopes are geometrically identical, and they are enclosed, right? And from there you get the word closed pair, right? And from the closed pair of form, I am inferring that is giving rise to the idea of form closure, right? Nowhere else it has been described that explicitly and neatly. So from there, I take that is the intention, that 3 elements are there. There are form, there is identical geometry, and there are enclosure. What he says is that one is hollow, the other is open, right? And then he I'm saying that determination of closed pair, right? Here you notice that he mentions that slide on one another, right? As things are enclosed and they move, one will slide against one another, right? So the motion, what he developed earlier in terms of rolling of two centroids, has been now completely abandoned, because he's coming from the motion perspective, giving the form, interaction, etc., right? Here he told that rolling one centroid upon the other gives rise to my desired motion, right? And here that has been abandoned and adopted that one form slides over the other. Okay, so now when I'm talking about that motion's kinematic pair, general motion of rigid body is rolling or moving centroid over a fixed centroid, right? If you take that, rollamide gives me a potential thing where things will move over one another, but it will not, it can have a general motion, right? So the 3 things that come from here: closed pair, reciprocal envelope, geometrical identity, right? So this description of a lower pair, for me, it looks like more intuitive rather than an analytical derivation. So hence, all the examples or things you'll see that are proposed and then described. Here, this is a very important observation he makes, is that because this is a single constant motion, a most generic curve will be arbitrary curve like that, right? It will go arbitrarily. Then he says that if I take that arbitrary curve, locally I can define a finite frame, right? And a necessary condition is that it is the same frame that has to go over that because it's the same shape. Then he says that, okay, he describes it as a small shape that will be identical here and there, irrespective of what is the reference position. And this property of identity of that finite or say non-trivial segment that has to map at every location, right, is satisfied a condition only by a helix. Okay, and that is to a cylindrical helix. Okay, and from there he derives the first thing as a helical, as a entity. Interestingly, helical pair is not a planar pair, right? And he derives the concept based on a helical pair, whereas his focus remaining things that come is only for the planar systems, right? Where he says that, okay, this helix on the pitch becomes zero, they become circles, and I have these, and otherwise I have prismatic pair and things like that. And then he describes that what is the need for that kind of profile to constrain that from the form closed point of view, not from the pure geometry point of view. So this continuous symmetry and closure are two different aspects. And I just, for the sake of it, I thought that we should know the word photonomy, right? Not kinematics is what Rilo prescribed as a field of study. He says that Ampere proposed the word kinematics, but not in the sense that we are using it, right? So he says that no, whatever you're doing is about photonomy, please use that. Okay, so I'll also occasionally use this word. Okay. In the derivation, surface to surface overlap as a pair is sufficient, but not a necessary requirement, right? And this is my observations. Not only the points at the interface, but all the points in the moving link in the pair trace the curves of the similar class, right? Why consider only the interface? All the points in the second link will move the same class. Homologous points are constrained to remain in one of the family of curves during their motion, and locus of the homologous points on the link is governed by the instance of the family it belongs to. And if you take that, we can define the 6 pairs not based on the surface-surface interaction and contact, but the locus of the points the moving body have. If it is all the points are moving in concentric circles in parallel planes, then it becomes revolute pair. If they are parallel straight lines, this prismatic pair. If they are coaxial helices of same pitch, it becomes helical pair. Coaxial cylinders, cylindrical pair. Concentric sphere, spherical pair. And parallel moves in parallel planes, then it is a planar pair. Why this is important is that that helps us to not only both analyze but also synthesize the kinematic. These places, in fact, is implicitly used by all their endeavors to close the pairs for a given motion. Not only me, but even they actually use that as the characterization. In the screw, he himself mentioned, in the screw, all points in the nut describe helices and equal helices if the describing points lie at equal distances of the helix. So, it is all there. And then he mentions that restraints ensuring relative motion defined by loci of points. So from there, whatever, I get that form closure is therefore not about form at all, right? Form closure is not about forms, not about forms that are closed. It is about surface-surface contact, not necessary in lower pairs, right? And it is about ensuring the characteristic of the inversion invariant relative motion through persistence of contact, right? So, and that is the characterization of lower pair. Okay, now what do you do with that? Shape, contact, and photonomy, which I am calling, say, kind of magic. Given required motion, find possible shapes and contacts, which is restraints, right? Or we have a given shape and contact and find possible motion. So this is the synthesis part. This is the analysis part, right? Motion. So motion based was by Rilo, and force equilibrium based was by Lakshminarayana. For the same thing, given required motion, find possible shapes. And there is no surprise in this case at a very at top level. I don't want to undermine anything, that it is now known that the forces and velocities are dual in their all behavior. So whatever we can analyze from contact, normal, and things like that, which is forces, which is like force, the motion velocity type of thing, can also be sort of done by forces. Yeah, and find order of motion, and find order of shape, and the shape tangent, and which is sort of intuitive and common practice. And volume of research, who use that, right? It is not the pure kinematicians. It is the robotic community that use that result maximum in grasp synthesis. Given a robot, how to grasp an object, which should be the points of contact, such that it will not slip away, in which case the form closure is maximally used. And also, the second part, maximally used by form closure, force closure, are in the medicine, right? Who are studying the musculoskeletal systems, or the defined joints and their ligament and the structure and things like that. There you'll find maximal use of the word form closure and force closure, where there is an underlying bony phase where the two motions are constrained in a certain way. There is a form based, there is a form closure, and if maintained in position because of the other ligaments tied to that, therefore there is a force closure there, right? Term force closure is otherwise not that much prominently available in mechanisms domain, if you like. Now, second part is given shapes and contacts, that is restraints, find possible motions, right? I give arbitrary two shapes, say that they're in contact, what kind of motion they'll exhibit. Okay. And here also we'll see the two works that I'll primarily see. This is my focus. The two works, the geometric and second order kinematic analysis, is taken into account by two works. By one is Avinash, and other is Ramakrishna. Okay, so this is the analysis of Relo, single point restraint, the formalism that some contact, some restraint of translation, if they're in contact, these translations are available, this translation not available. And when we are having a point same contact and we're exploring rotation, he defines that, right side and left side, right? Here the clockwise motions are possible, counterclockwise not possible that way. They are of two different types. And that is what is then composed to identify the effect of multiple contacts and the available motion, which in turn gives you the immobilization or. So this is the analysis method, if you like, and then we see that case of translation, and these are the two domains. This is the still in this direction it can come out, and then if you have to another contact, if it is on that side, it is ineffective. Although there are three contacts, it doesn't stop anything. But if I give it on the other side, it is a restraint which is effective. Now this part I can see, right? But now we can talk also. But from here, you can see that minimum 3 suitably placed contacts are needed to restrain translation, and minimum 4 suitably contacts are needed to restrain rotation. These are the results from Relo's this contact-based and the motion space-based analysis. Then he goes to this 3-dimension, and also what I'm showing here is that analysis always starts with a sort of a primitive form. Prismatic means start with a prism, right? Revolute or cylindrical means start with a cylinder, and helical means start with a helix as a form. And then you see how can I think about that. Okay, from there he shows that for a revolute joint to make out of this, you need say some points on the surface and some points on the two ends, right? And then he says that okay, that is fine. It requires seven points, but 8 points here is sufficient. But if I arrange them in a different way, it can be managed with 6 points. Okay, so that is how the type of thing. You see that again, this is very, very intuitive development, where he also says that like that for a helix, I need about 8 points are necessary to constrain a helical surface in its position and still have that property of helix, that rotation linear motions are there. Okay. This is improved upon in some sense by Professor Lakshminarayana, where he showed that a revolute pair can be obtained with only the 6-point contact through this thing. And it also shows that different kinds of joints in using the force and there's the closures point of view. Helical pair, either in here, analytically part, it seems to be difficult to handle analytically. Right. And my hypothesis on that is that the helical surfaces are sort of, transcendental. So it is difficult to capture it in terms of directly equations, which can also represent the second order surfaces like cylinders and spheres like that. Okay, so these two request two different paradigms in that sense. Okay, so now I will come to the basics. The work that Avinash did here. The primary focus was that contact configuration for lower pairs with variety of forms in contact. As you said, the surface-surface contact is not necessary. Then arbitrary form if I give, and they say that they are going to assemble, then I cannot directly say that the surface-surface contact will be there. If any other type of contact is there, will it give me that kind of the motion? It has got two parts: characterization and recognition. That means if they're assembled and that kind of joint is there, I know this kind of joint, then what is the relationship? And given an arbitrary system, I check whether the relationship is satisfied or not. That becomes an application domain recognition. That I have CAD models, I said this goes there, and then I take this set of features like surface, points, lines, etc., and then see whether those characteristic conditions are satisfied or not. And that way, I can get this recognized. I'll quickly go through that. The cylindrical. How much time has gone by now? Okay. Yeah. So this is the classical cylindrical pair, and you see that I can have a cylindrical pair with a arrangement like this also. In that case, you see that condition is that convex cylinder of radius r and three planar faces parallel to the axis at a distance of r. This is the characterization. Now, if I use this characterization and this two disparately located things are there, like this is a second part, I can have some planes and check if I do the offsetting by the intended radius r, are they co-intersecting? Right. Two planes give a line. So two at a time, I'll get three lines. If all the three lines are same, then I can put a cylinder there, it will be in contact. Right. And in between, if there is another plane, right, which is at a lesser distance, I can say that no, although that will admit, but this one will interfere. That means actual assembly will not be possible. That means even if other planes are there, they have to be at a greater distance than this where I want to assemble. That way, I can also identify in a given set of such faces where exactly this particular cylindrical object can be placed. So there is the assembly problem. And because it's a cylinder, already I decided, therefore I know that that will be the axis, and I know what is the local coordinate frame of that. Okay, so this is what it is. And for other things, I can have similarly, I can have not planes but surface the different kinds of surface and points and things like that. Okay. And similarly, by offset calculation, I can also recognize certain kind of things. Okay, different kinds of combinations. And I wanted to focus on few special configurations that this is also a cylindrical pair. Okay, only a line contact along a circle and a cylinder. This will make a cylindrical pair. Okay, and this one will also make a cylindrical pair. I say that cylindrical pair without a cylindrical element. Right? Behavior is cylindrical, but there is no cylinder here. I have some circles and three lines. It is essentially three parallel lines and two circumcircles. Right? It can be easily recognized. It can be easily manufactured. But there is no need for having that straightness and cylindricity and all this stuff. I can still get a very good cylindrical pair. Do not ask about will it be sufficiently load bearing at this moment. Okay, this is pure kinematics. We can do that. Similarly, this case, which is a cylindrical pair, right? But it doesn't solve. But it is that it is physically realizable where the conical surfaces and contact the cylinder along a line. But in terms of the axis and things like the radius, it is very difficult to characterize and recognize, but this can also be handled. Okay. Now, spherical pair. Here also, these are sphere inside sphere, we know standard, right? But other things are also, this is a circular arc contact and things like that. We can get these spherical pairs. And this is, if I have sphere in contact with multiple flat faces, I can find the center. But this is more curious, that this has got spherical behavior, but it doesn't have any sphere. It can be done in pure turning, right? Without any form tool, right? It's a pair of circles, spherical pair without any spherical component, essentially two pairs of circles. Okay, we can get that. And actually, I had a prototype of that, but due to my lab shifting, that got misplaced. Yeah, it is there, but I don't know where. All missing things are like this, they're there, but I don't know where it is. Yeah. So similarly, prismatic pair, and this is similarly a planar pair without any plane. It is nothing but a three pairs of lines, right? Two below, one above. It is a purely form closed planar joint, right? No matter to what shape these lines belong, or they're simply straightened rods or wires, it will still be a planar pair. And from there, what we can generalize is that give me a set of wires which I can bend in a certain form, all kinds of joints can be made from that, right? The points of contacts in this case, you see, are not preserved. Identity of the points are not preserved. Okay. So contact therefore refers to the contact between the parts, even if the contacts keep shifting continuously or discretely. These things I still have not, do not know how to describe it in terms of that. What kind of pair is this, right? But motion is very definite, right? Okay. Now, very quickly to the next level, that given up to this was done, then the problem was that in a system like this, if you give arbitrary shapes, which has got knot surfaces, and I give them in contact, what kind of pairs it will make. So with that thing, we went that, okay, first was that if I have these three situations, the first order analysis based on the normals and tangents, they don't distinguish. But anybody can say that this will come out, this will maintain the contact, and this will not move at all. Right. That means something more is necessary. And this goes to the in the surface context, that same behavior means the first order means that normalcy and normal and tangent relationships, but one may give you a revolute joint, one will give you a sort of a prismatic joint, and this will give you a planar joint. Right. So therefore, more understanding is required in terms of the interaction of the forms in contact. Right. Now, I believe that there is a paucity of time, so I'll quickly just run through the slides, okay, to indicate that there is a great deal of mathematics required here, and I can confess that in terms of the algebraic manipulation of symbols and all, I'm not very clever, right? I trust my student on this, right? And the geometry level I can interpret, okay? So here you see that this is the fundamental of the situation, that if one part is fixed, other part moves, these are the three phases. Either it will penetrate, or it will separate, or it will maintain the contact. The motion is arbitrary, and the arbitrary motion, if you take, then there is the second order formulation, because first order was insufficient. Then you describe this system in terms of the point locations and their motions and things like that. And then it comes down to this formulation, the local geometry of smooth forms, and this becomes the x and y coordinate locally described like this. And then truncate up to the second order, we get this as the local definition of the shapes in contact, and they are having arbitrary motion between them, and description of the motion shape and the motion if you superimpose, right? Then we get this in terms of the screw coordinates and the derivatives, and then finally boiling, taking the only the algebraic manipulation, and then getting to the form which is coming to this, right? This delta t, which is a determinant of that matrix in terms of the at square plus bt, where a, it comes up like this, where km is the curvature of the moving profile, kf is the curvature of the fixed profile, and then remaining things are interpreted. Then using this existence of solution, we have to have this as to be certain characteristic, right? We should be able to compute the discriminant. And based on that, we see that these different categories can exist. And you notice that whenever B is not 0, it has got penetration or separation, which is not making any kinematic pair. Hence, B is equal to 0 is the first context of going for further studies. So A governs the second order characteristic of in context. Okay, and that's how this is formulated. And then for the situation like this, and you see, we get to the point that arbitrary thing like this can come here. Ultimately, what we get is that any motion that is there, I'll get equivalent polodes and pole location for which there will be certain kind of motion. So in this particular case, eventually what we'll get is that along the M curve, which is the condition of point about which you are rotating, is the fundamental thing about the B is equal to 0. Okay, and all A is equal to whatever is on that, and that will decide whether it is positive or negative, and then whether it will be separating or interfering kind of things. Based on that, when you analyze, you get that in this particular case, you will have these R1 and R2 values like that. And if the center is taken, center rotation is taken anywhere in the red, it will not allow it to penetrate. And if you take the centers and the blue regions, which is marked 4, right, it will allow, it will either persistent contact or separate. And that way, it distinguishes between all these cases. Okay, and now if we compose, we can show that what kind of, that this will not move because these are the motion allowed regions, right? And here, other two are not allowing. So a particular motion is about some point is possible only if all the contexts allow it. And considering that, to further studies, we you can synthesize kinematic pairs of different types by placing those CM and CF differently, and different types of joints can be synthesized. Okay. Then the same analysis is taken to a surface context, and similar this thing that we first locally define the shape and as a second order approximation, and then consider the motion, arbitrary motion, right? And using the same type of the screw and screw derivatives as the thing, we lot of algebraic steps, and finally, comes to the point that I need to have characterize this something called D, and in that, for existence of solution to the above equation depends upon the nature of D. Now here, existence of solution means the two surfaces are intersecting. Only then I have a contour. So here this existence of solution is when this is not interfering. That means the surfaces should not intersect. So then it becomes that all these algebraic things showing that finally it comes down to this: the first order, first leading principal minor is positive, second one is also positive, therefore ultimately it depends upon the third one. So first two principal minors are positive, therefore if D greater than 0, then D is positive definite and non-trivial solution do not exist, right? That means they'll intersect, right? And therefore either indefinite or positive is required, then we need to have D is equal to less than 0 or D is equal to 0. Equal to 0 means persistence of contact, and less than 0 means separation, based on which all other characterization again comes back to the similar argument, and then we can distinguish between these three situations of, say, this particular motion is imposed, right, which is basically giving a motion along a given direction, right, y direction, and then you see that you get the results as distinct, right, and it shows that in the first case, this becomes positive, that means it will separate, and other case this will maintain, and the third case it will be separating. So you see that in the first case and third case, this motion will separate, in the second case it will be maintained. Okay, through this analysis we can distinguish now between the three different situations of form closure, first order form closure, second order form closure, and kinematic pair. And then I'll directly come here that if a form is there, two spheres are put there, and from here we can do the analysis and finally get this situation that all the screws are 0 except the NA rotation about the common normal axis, right, is non-zero, That means this is only a rotation is allowed. Therefore, this becomes a two contact. Like that, we are getting a revolute pair. Okay, and this similarly will show that this forms a prismatic pair. Planar pair, right? And this one can be shown as these three situations, that these two are form closed, right, with only 3 points. That is because the shortcut saying that these lines must co-intersect. If the lines co-intersect, then I get this, right? With 3 point, I can get a form closure here. Here I have 4 contacts, they are co-intersecting here, then get a form closure, okay, and I can get that, okay. And here it is not form closed, right? But in this sense, it is form closed. It cannot violate the contact persistence, but it can still have 1 degree of freedom motion there. I'll close it by showing this example where these two are not spheres, right? In that case, I can take Dupin indicatrix, and here the two major axes, if I align from here on the right side this much and left side that much, rotation can be possible at every contact. By suitably aligning their Dupin indicatrices in some sense, right? I can have the allowable motion here is restricted motion here, and restricted motion is a allowed motion here, right? In that case, I can get a form closed, second order form closed of the solid, right? Any surface, only with 2 contacts. Only condition is that I should have a common normal available, which is has a pedal point or some name is there, right? But existence of such points is not always guaranteed. But if I have that, right, by suitably changing their curvature profiles, only with 2 points, a rigid body can be immobilized. Okay, with that, I'll close this. Further questions are there that still now we do not know how can a 4-point contact can give rise to a screw motion, right? So that is something still thing is possible, but only thing is that can contact be associated with screw and non-zero pitch? Helical surfaces contact do imply a possibility, but helical surface is not in point contact, right? There is surface contact and things like that, right? And in terms of point contact, it requires at least 4 points. Therefore, multiple points simultaneously, if I can consider possibilities there, chance. What happens when Dupin indicatrixes intersect? We went up to only when it is in contact, right? If it intersects, then what kind of motion emerges from that? Those things we can think about. And with that, I'll close my presentation. Thank you.
Thank you, Professor Sain, for a wonderful talk. I will open the floor to questions. We can take a few.
I was going to ask about a kinematic abstraction. I didn't quite get that part.
Yeah, so I have a lot of details in terms of form, right? Abstraction is that it doesn't matter if you simply put a point there, it describes the relative motion. So that is the abstraction. Abstraction is about getting rid of unnecessary details. Okay, overall shape of the link doesn't matter, because if I know the motion of 2 points on the rigid body in a plane, then I know the motion of the whole plane, of any other point in the plane. Hence, we'll consider only 2 points, right? Like that is the notion of kinematic abstraction.
Thank you for this presentation. So regarding the number of point contacts and the degree of freedom of the motion, we have a relation, I think, because in Hunt's book, we know that every point contact means reciprocally it's a force constraint. So if we want
Yes,
5 degree,
I
1 degree of
understand. So
freedom
that is
motion,
where this subject takes it somewhat forward. First thing is that is referred to as first order study,
okay.
which cannot explain all the situations, which is stated that, you know, the 3 cases, if it is there here, yeah, suppose here, right, it will not explain why something they are behaving differently. Okay, when you have multiple contacts also, we find that although the contact configuration is similar, actual motion behavior is different. Okay, that means there is something more to this than only from the point contact. right? When you're saying point contact defines that, we do not give directionality. It means that those 2 points are inseparable by definition. That means a force can be either going through it or against it. They do not separate. Okay, but you note that any contact gives resistance only in one direction if it is like a compressive kind of load in that sense. So that is not covered in that equation.
That's
Yeah, so that's why all these complications arise.
thank you.
Devak, a great talk. How far are we from your goal of getting objects made in SolidWorks or any CAD package,
Okay, so that part I did not
automatically detecting
include.
the
Yeah, actually,
pairs?
the whole the student's work involved that. So he had demonstrated in SolidWorks. So he did that, the sort of a click, click, and assemble kind of thing. It was they call it Visual Basic kind of interface. At that time, it was a more sophisticated interface was not available. Except SolidWorks, nobody else was providing an API to their CAD model. So you can model it, but you cannot query that model in terms of this building entities like point line, etc. But if I have to do that, I have to go more down level where the GUI is not available, like a set file format and things like that. I can get access to the primitive features, but there is no GUI level support, right? So nowadays these are available, it can be done. But as a part of his thesis, he had to demonstrate that given the parts, he'll click, click, click and assemble it, and directly his output will be 2 files. One is a CAD assembly, other is a CMD file that can be read by Adams. And no further input will be required. I can directly run that file in Adams for analysis. So that was already done then.
Thank you.
Thank you very much. We will have a photo session after we have presented the mementos to Professor Sain. I would like to request Professor Sandipan Bandyopadhyay to be on stage for presenting both the memorial lecture memento as well as one from the organizing committee. And Safwan would play a video which shows what the mechanism does. So that's the memorial lecture memento. It's actually Lakshmi Narayan Memorial Lecture. And here's a video showing what it does.
The memento presented to Professor Divakar Sen shows two intriguing concepts from the work of late Professor K. Lakshminarayana. The letters K and N are free to move without the letter L. The letter K forms second order form closure with letter L, where they share a common curvature tangent, whereas N forms a first order form closure with a common tangent only. Hence, the letter K has a small play and the letter N has a larger play.
AMM also has an honorarium alongside the memorial lecture memento. Thank you very much, Professor Sain. Thank you, Professor Bandyopadhyay. Um, I'd request all of you to be on the dais for a quick photo.
Thank you very much. We have SMDC posters and also the regular poster right outside where we had tea earlier. And then we'll proceed for lunch from there. We will meet back in the seminar halls 1 and 4 for the technical sessions of the afternoon. Thank you very much.